You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Freshness in retrieval systems refers to the degree to which indexed content reflects the most recent and accurate version of underlying source data. In other words, it measures whether what a user retrieves today matches the current reality of the information source. A system that indexes web pages but takes weeks to incorporate updates cannot be considered fresh, since queries may surface obsolete details. Freshness is a moving target because data constantly evolves. News articles are updated, compliance regulations are amended, and product catalogs expand daily. Retrieval systems that fail to track these changes risk returning outdated answers, undermining their credibility. Thus, freshness is not simply a desirable feature, but an essential quality for modern retrieval pipelines, especially in environments where timeliness directly affects decision-making. The importance of freshness becomes clear when considering user trust and accuracy. A search engine that shows last week's news as if it were current erodes user confidence quickly. An enterprise system that retrieves outdated policy documents may lead employees to act on obsolete rules. Even in consumer contexts, stale results can frustrate users, for instance, recommending products no longer available for purchase. In high-stakes domains like finance, medicine, or law, the cost of staleness is even greater, as relying on outdated information can cause regulatory breaches or harm. Ensuring freshness is therefore not merely about convenience, but about maintaining the reliability, accuracy, and usefulness of retrieval systems across all domains. Incremental indexing is one of the core strategies to maintain freshness. Instead of rebuilding an index from scratch whenever data changes, incremental indexing updates only the parts affected by new or modified content. For example, if 10 new documents are added to a knowledge base of millions, incremental indexing inserts only those 10 into the index. This approach minimizes downtime, reduces compute costs, and ensures that updates can be propagated quickly. It is the equivalent of adding new books to a library catalog without recataloguing the entire collection. Incremental indexing thus provides a foundation for scalable freshness, enabling systems to adapt continuously without overwhelming infrastructure. Streaming document ingestion builds on incremental indexing by enabling near real-time updates. Rather than waiting for scheduled batch jobs, pipelines can ingest documents as they arrive, embedding them and inserting them into indexes almost immediately. This approach is critical in domains like news search or compliance monitoring, where delays of even minutes matter. It resembles a live news feed. As soon as news stories are published, they become available to readers. For retrieval systems, streaming ingestion ensures that answers reflect the most current information without waiting for batch cycles, creating systems that are responsive and alive to ongoing change. Time to live (TTL) mechanisms provide another tool for freshness by automatically expiring data after a set duration. Each piece of content is tagged with a lifespan, after which it is removed from the index unless refreshed. This ensures that outdated or irrelevant information does not linger indefinitely, cluttering search results. TTL policies are especially useful for transient data such as job postings, event announcements, or pricing updates, which become misleading once expired. TTL acts like a self-cleaning filter, automatically maintaining freshness by pruning stale content. It reduces the risk of outdated results while lowering the burden on manual oversight. Event-driven updates ensure that indexes remain responsive to changes in source data. When a document is created, modified, or deleted, the event triggers an update to the retrieval index. This approach contrasts with blind periodic updates, focusing effort precisely where it is needed. Event-driven designs are particularly effective in environments with well-structured data pipelines, such as enterprise systems connected to databases or content management systems. By linking retrieval freshness to actual changes, event-driven updates reduce unnecessary work and ensure alignment between indexes and source systems. Batch versus real-time updates highlight another key trade-off in freshness strategies. Batch updates are efficient, bundling many changes into a single process, reducing overhead. Real-time updates, however, prioritize timeliness, ensuring changes are reflected immediately but at the cost of higher processing frequency. The choice between them often depends on the use case. Financial systems may demand real-time indexing, while internal document repositories may tolerate hourly or daily batches. Many organizations adopt a hybrid approach, combining batch ingestion for routine updates with real-time ingestion for high-priority changes. This balance ensures efficiency without sacrificing freshness where it matters most. Challenges of freshness scale exponentially as data volumes grow. Maintaining up-to-date indexes across billions of embeddings or documents is no trivial task. Each update requires computation for embedding generation, index insertion, and sometimes rebalancing or sharding. Scheduling these updates without disrupting query responsiveness becomes increasingly complex at scale. Additionally, freshness across distributed systems requires synchronization, ensuring updates propagate consistently across nodes. This complexity demands robust engineering strategies, balancing timeliness with cost, latency, and reliability. The scale challenge highlights why freshness is one of the hardest problems in modern retrieval pipelines. The impact of staleness on retrieval quality is direct and measurable. A retrieval system that serves old information may mislead users, leading them to wrong conclusions or decisions. Outdated answers reduce confidence in the system's outputs, even if only a small percentage are stale. Once trust is lost, users may abandon the system altogether. In applications like compliance, stale retrieval is more than inconvenient. It may result in legal exposure. Freshness thus directly determines retrieval system value. Without it, even the most sophisticated search algorithms are undermined by old, irrelevant results. Engineering complexity is unavoidable in building freshness-aware systems. Real-time ingestion, incremental updates, TTL enforcement, and distributed synchronization each add layers of infrastructure overhead. Engineers must design pipelines that can handle variable update loads, ensure fault tolerance, and monitor freshness continuously. Costs escalate as update frequency rises, forcing organizations to weigh freshness against resources. Freshness, therefore, introduces operational burdens that must be managed strategically. The complexity is not merely technical, but organizational, requiring coordination across teams responsible for data pipelines, indexing systems, and retrieval models. Monitoring freshness requires metrics beyond traditional retrieval benchmarks. Pipelines must track content age, measuring how long documents have been in the index relative to their latest source version. Update lag, the time between a change in the source and its reflection in the index, becomes a key performance indicator. Dashboards may track percentage of documents within freshness thresholds, enabling proactive maintenance. Without monitoring, systems cannot know when staleness sets in, leaving them blind to risks. Monitoring for freshness is therefore not optional, but a core component of retrieval pipeline reliability. Latency considerations create another balancing act. Rapid updates are desirable, but indexing pipelines consume compute resources that could otherwise serve queries. If update processes slow query responsiveness, user experience suffers. Systems must therefore allocate resources intelligently, often separating update workloads from query-serving workloads. Achieving freshness without degrading query latency requires careful architecture, such as using streaming pipelines in parallel with retrieval indexes, or adopting distributed systems to isolate workloads. The challenge is to ensure updates and queries coexist without stepping on each other's performance. Consistency versus availability is a well-known dilemma in distributed systems, and freshness management is no exception. Strong consistency means updates appear everywhere immediately, but this often requires sacrificing availability during synchronization. Eventual consistency allows updates to propagate gradually, maintaining uptime but risking temporary staleness. Different applications make different trade-offs. A compliance system may demand strong consistency, while a consumer search engine prioritizes availability. Freshness strategies must navigate this tension, ensuring the system meets its reliability requirements while minimizing outdated content exposure. Applications of freshness strategies span a wide range of industries. News search engines must deliver the latest headlines, ensuring stories appear seconds after publication. Legal systems must update with new statutes and case law, keeping practitioners informed of evolving precedents. Compliance monitoring requires freshness to detect new risks as regulations shift. Even consumer applications like e-commerce rely on freshness, ensuring product availability and prices remain accurate. In each case, freshness underpins trust, relevance, and utility. Systems that cannot guarantee up-to-date information simply cannot serve their users effectively. Finally, freshness strategies must connect with retrieval evaluation frameworks. It is not enough to test relevance in isolation. Retrieval systems must be assessed on both relevance and timeliness. Evaluation datasets may include time-sensitive queries measuring how quickly systems adapt to changes. Without explicit evaluation, freshness risks being neglected in favor of accuracy alone. Retrieval evaluation frameworks therefore need to integrate freshness metrics, ensuring that timeliness is treated as a first-class property of retrieval quality. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Incremental embedding generation is one of the fundamental tasks in keeping retrieval systems fresh. Whenever new documents are created or existing ones are updated, their text must be passed through embedding models to generate vectors that represent their meaning. These vectors then need to be inserted into the vector index, replacing or augmenting older entries. Unlike initial bulk embedding, which can be run once at system launch, incremental generation happens continuously and often unpredictably. For example, an e-commerce site may update prices hourly, while a news portal publishes new articles every few minutes. Each change must propagate through the embedding pipeline without overwhelming infrastructure or slowing down query serving. The challenge lies in balancing throughput, how many embeddings can be generated per second, with latency, ensuring updates appear in indexes quickly enough to be useful. Organizations often solve this with parallel pipelines, where embeddings are generated in one stream while queries are served in another, ensuring freshness without bottlenecking performance. Index sharding adds another layer of complexity to maintaining freshness. Large retrieval systems distribute their indexes across many machines or shards, each responsible for a subset of the embeddings. While this improves scalability and allows systems to handle billions of vectors, it complicates updates. When a new embedding is created, it must be routed to the correct shard, inserted, and synchronized with replicas. If shards update at different speeds, users may see inconsistent results depending on which shard serves their query. Synchronizing freshness across distributed shards requires sophisticated coordination protocols. Systems must choose between strong consistency, where all shards update simultaneously but may temporarily block queries, and eventual consistency, where shards update asynchronously but may serve slightly stale results. The design choice reflects the trade-off between immediacy and availability, one of the defining challenges of freshness at scale. Change data capture (CDC) pipelines are increasingly used to connect data updates directly to indexing systems. CDC works by monitoring source databases or content stores for changes, such as new rows inserted, updates applied, or deletions executed. These events are then streamed into the indexing pipeline, ensuring updates propagate automatically without relying on scheduled scans. For instance, when a financial database records a new transaction, the CDC pipeline triggers embedding generation and index insertion within seconds. This tight integration ensures retrieval indexes remain synchronized with their underlying data sources. However, building robust CDC pipelines requires careful handling of data volume spikes, ensuring that bursts of activity, such as a major news event or flash sale, do not overwhelm downstream systems. It also requires resilience against errors, since missing a CDC event can leave stale data lurking in indexes indefinitely. Streaming platforms provide the backbone for large-scale ingestion of freshness updates. Tools such as Apache Kafka, Pulsar, or AWS Kinesis, function as message queues that buffer incoming changes and distribute them to indexing services. These platforms are designed to handle millions of messages per second, making them ideal for environments where freshness must scale globally. For example, a multinational social media platform may receive updates from users in every time zone, and streaming platforms ensure these updates are processed in near real time. Embedding models and indexes then consume these streams, generating vectors and inserting them into storage incrementally. By decoupling data ingestion from processing, streaming platforms smooth out bursts of activity, preventing system overloads while preserving timeliness. Without such infrastructure, large-scale freshness would collapse under unpredictable loads. Time to live, TTL policies translate the abstract idea of freshness into an automated mechanism. With TTL, each indexed document is assigned an expiration period, after which it is automatically removed unless refreshed. This is particularly useful for data with inherent temporal boundaries, such as stock prices, weather forecasts, or event listings. Once the TTL expires, outdated entries are purged, ensuring that users do not see stale results. TTL can be tailored per domain. Legal documents may never expire, while a news article might have a 48-hour TTL before being deprioritized unless explicitly updated. This automation reduces manual oversight and enforces freshness, even in the absence of constant updates. The downside is that overly aggressive TTLs can prematurely remove still relevant documents, while overly lax TTLs may allow stale data to persist. Designing TTL requires balancing domain knowledge, user expectations, and operational cost. Re-indexing strategies remain necessary even in incremental pipelines. While many updates can be handled by inserting or replacing individual embeddings, certain changes require rebuilding entire sections of indexes. For example, when upgrading to a new embedding model with different dimensionality, all documents must be re-embedded and reinserted. Similarly, when large volumes of data are reorganized, such as restructuring product catalogs or migrating legal archives, incremental updates are insufficient. Full or partial re-indexing ensures consistency but comes at a high computational cost. Organizations often schedule these heavy re-indexing jobs during off-peak hours, staggering updates to minimize impact on user queries. The coexistence of incremental and full re-indexing reflects the dual nature of freshness. Continuous light updates handle the everyday churn, while periodic heavy updates ensure alignment with major shifts. Evaluating the impact of freshness requires more than measuring query latency or retrieval precision. It involves tracking how retrieval accuracy changes over time as data evolves. For instance, a retrieval system may perform well immediately after indexing, but degrade steadily as new documents appear without being incorporated. Freshness evaluation thus measures the decay of retrieval quality, quantifying how quickly systems fall out of sync with reality. Common metrics include update lag, the time between a data change and its reflection in search results, and the percentage of documents within a freshness threshold. Evaluation ensures that freshness strategies are not simply deployed but validated, providing feedback on whether they meet organizational goals. Without such evaluation, freshness risks being treated as invisible infrastructure until failures become obvious to users. Human-in-the-loop processes can complement automated freshness pipelines in high-stakes domains. In law, medicine, or compliance, updates may require expert review before being indexed to ensure accuracy and appropriateness. For example, when a new legal precedent is published, lawyers may annotate its metadata and validate its embeddings before insertion. Similarly, in healthcare, clinical experts may review updates to medical guidelines before they are exposed in retrieval systems. Human oversight adds latency, but ensures that freshness does not come at the expense of quality or safety. It also helps detect anomalies, such as false updates or malicious data injections, that automated pipelines might miss. By combining automation with human review, organizations create retrieval systems that are both fast and trustworthy. Security implications of freshness often receive less attention but are critical. Stale indexes may continue to expose sensitive or outdated confidential data, even after it has been deleted or revoked from source systems. For example, if an employee's private HR record is removed from the database but lingers in the retrieval index, unauthorized queries may still surface it. Similarly, compliance-sensitive financial data may remain accessible long after policies demand its deletion. Freshness strategies must therefore include mechanisms for secure deletion, ensuring that sensitive information disappears from indexes in lockstep with its removal from source systems. Failure to align freshness with security creates both legal risks and reputational damage, making secure freshness an essential design requirement. The cost of maintaining freshness is often significant. Real-time pipelines consume compute cycles for embedding generation, network bandwidth for streaming updates, and storage capacity for maintaining growing indexes. Organizations must weigh the cost of immediate freshness against the value it delivers. For example, a news platform may justify the expense of real-time updates, while an academic archive may prefer batched weekly updates to conserve resources. Cost also influences engineering decisions. Smaller organizations may lean on TTL policies and batch updates, while larger enterprises invest in full streaming infrastructures. Every gain in freshness carries a price in infrastructure, making financial sustainability a core concern alongside technical feasibility. Trade-offs in real-world systems often force organizations to balance perfect freshness with operational efficiency. Perfect freshness, ensuring every update is reflected instantly, is rarely attainable at scale without prohibitive cost. Instead, organizations adopt prioritization strategies. Critical data streams receive near real-time updates, while lower-priority content is updated less frequently. For example, financial transaction systems may update continuously, while background knowledge bases update hourly or daily. This pragmatic balance ensures resources are allocated to where freshness matters most, reflecting the reality that not all information requires equal timeliness. Recognizing and codifying these trade-offs is key to building sustainable retrieval systems. Benchmarks for freshness are emerging to test how well systems handle update lag and retrieval latency under dynamic conditions. Unlike static benchmarks that measure accuracy on fixed datasets, freshness benchmarks simulate streams of updates, measuring how quickly indexes incorporate changes and how retrieval performance degrades without updates. These tests are increasingly important as retrieval systems integrate into real-time workflows. They provide empirical evidence for comparing strategies such as incremental indexing, streaming ingestion, and TTL enforcement. By standardizing evaluation, benchmarks help organizations quantify freshness performance and justify investments in infrastructure. They also push the field toward treating freshness as a measurable, competitive property rather than a background detail. User trust is directly tied to freshness. When users consistently see up-to-date results, they build confidence in the system's reliability. Conversely, encountering outdated or misleading content even once can damage trust disproportionately. In enterprise contexts, employees may bypass internal systems altogether if they believe they cannot rely on freshness, undermining adoption. In consumer contexts, stale recommendations or search results drive users to competitors. Trust is fragile, and freshness is one of the clearest signals of whether a retrieval system respects user needs. Maintaining freshness is therefore not only a technical responsibility but also a user experience imperative that influences long-term adoption. Emerging techniques are making freshness pipelines more adaptive. Rather than refreshing all documents equally, systems selectively prioritize updates for high-value or frequently accessed content. For example, news articles receiving heavy traffic may be re-embedded more frequently than rarely visited pages. Adaptive pipelines can also adjust refresh frequency based on query logs, ensuring that documents tied to trending topics remain maximally fresh. This selective approach conserves resources while focusing freshness where it matters most. Combined with predictive analytics, Adaptive pipelines can even anticipate which content will soon need updates, proactively reducing staleness before it becomes visible. These innovations show how freshness strategies are becoming smarter, not just faster. Looking to the future, freshness will only grow more critical as AI systems integrate with dynamic, real-time data streams. Retrieval-augmented generation, for example, relies on indexes that reflect the most current knowledge available. As AI moves into domains like financial forecasting, cybersecurity monitoring, and real-time decision support, the tolerance for staleness shrinks. Freshness will no longer be a nice-to-have, but a baseline requirement for system credibility. Future pipelines will likely combine adaptive, streaming, and event-driven approaches with automated compliance checks and human oversight, creating ecosystems that are simultaneously fast, secure, and trustworthy. The trajectory is clear. As AI systems operate closer to the real world, freshness will define their relevance and reliability. Finally, Episode 17 connects directly to the next stage of our exploration: evaluation frameworks. Freshness is not meaningful in isolation. It must be measured in terms of retrieval performance. Episode 18 will examine how evaluation frameworks test not only relevance, but also timeliness, showing how freshness strategies manifest in real-world results. Together, re-rankers, freshness pipelines, and evaluation tools create the scaffolding for retrieval systems that are accurate, responsive, and trustworthy, ensuring they remain aligned with both user needs and dynamic information landscapes. In conclusion, freshness at scale demands a complex mix of incremental embedding generation, streaming ingestion, TTL enforcement, and adaptive update strategies. It introduces engineering complexity, operational costs, and security challenges, but it is indispensable for user trust and retrieval quality. Whether in consumer search, enterprise compliance, or real-time monitoring, freshness ensures systems reflect the present rather than the past. As benchmarks, adaptive pipelines, and human oversight evolve, freshness will become one of the defining measures of retrieval excellence in modern AI. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.